Hello, welcome back to another video on curve sketching. In this video we're going to use the first derivative test and concavity to sketch the graph of this function. You've probably seen this function in a couple previous videos, but now we're going to do it from scratch, start to finish, the whole thing. So what I want to first show you is it is my website. So if you go to this link, click on Calc 1 and then you can scroll down to applications of differentiation. And there's a section called Examples of Curve Sketching with step-by-step instructions, which is found in the second half of these notes. If you go ahead and click on it, it's a PDF. Scroll down about halfway. I believe it's page 11, around there. And we have something called Summary of Curve Sketching. And so there's a whole list of things that you need to satisfy to sketch a curve. Some of these aren't applicable to us because we don't have things like horizontal and vertical asymptotes with polynomials. But for right now, what we have to do is start with finding the x and y intercepts. So let's go ahead and do that now. So step 1, find the x and y intercepts. So to find the x-intercepts, you're going to take your function and set it equal to 0. Then we're just going to go ahead and solve it. So they both have a factor of x cubed. When we factor that out, we're going to be left with 3x squared minus 5. And then now that it's factored, you'd set each factor equal to 0. So x cubed equals 0. And then 3x squared minus 5 equals 0. Well, solving x cubed equals 0, that's just x equals 0. And here, we would just do some algebra here to solve this. So bring the 5 over, then divide both sides by 3. And this is going to give me two solutions. It will give me a plus and a minus square root of 5/3. Now the square root of 5/3 is roughly 1.29. Okay, so this gives me the following x-intercepts. We have 0, 0, negative 1.29, 0, and positive 1.29, 0. So there we go. Now to find the y-intercept, all we're going to do is plug in x equals 0 into my function. So if x is 0, then what do we get when we plug it in? We're going to get, I'll do it over here, 3 times 0 to the 5th minus 5 times 0 cubed. Well, that's just 0. So the origin is the y-intercept. We also found that to be the x-intercept as well. Next, we're going to find local extrema using the first derivative test. These were the steps in a previous video on the first derivative test. You would find f prime. You would set f prime equal to 0. Figure out when it doesn't exist. You draw a number line. You'd evaluate points from each region in the number line into the first derivative. And then you'd use this fancy table down here. So take a moment, pause. You can write down this information. It's extremely helpful. So let's go ahead and start this process now. So let's find f prime. Now remember that f was 3x to the 5th minus 5x cubed. So the derivative is just going to be a power rule. Which is going to give me 15x to the 4th minus 15x squared. So here's our derivative. So I already found it. Next, what we're going to do is set f prime equal to 0, or find out when it does not exist. Let's go ahead and do that. 15x to the 4th minus 15x squared. You're going to set that equal to 0. And then you're also going to look at when does 15x to the 4th minus 15x squared not exist. This is a question. Now since this is a polynomial, polynomials exist everywhere. So we're not going to have an issue with this. Polynomials are differentiable everywhere, so we're good. But we do have to solve this. What I see is I can factor out a 15x squared, leaving an x squared minus 1. If I factor this difference of squares here, we're going to get x minus 1 and an x plus 1. So we're going to get three critical values. We're going to get one from here, x equals 0. What makes this thing 0? That would be x equals 1. And finally from this piece, x equals negative 1. So now that I have my critical values, what we're going to do is do step 3, which is to draw a number line and plot those critical values. And then we're going to plug a number from each region into that first derivative. So let's plot our critical values here. Now it says pick a number from each region. I'm going to pick -3. It doesn't really matter what number you pick. I'm just kind of randomly picking numbers. 0.25 and 2. So what you're going to do is you're going to plug each one of those into the first derivative. So we're going to get 15 -3 to the 4th minus 15 -3 squared. And we're going to get 1080. Now that's greater than 0, meaning it's positive. So that means in this region, we are increasing. Remember, a positive first derivative means increasing. And let's go ahead and go to the next region, f of -0.5. And hopefully you see what I'm doing here. All I'm doing is just plugging in the numbers into the derivative. And plug that in correctly. We should get something like -2.8125, which is negative. So that means we're going to have a minus sign here. It's a big minus, which means we are decreasing in this region. Now I'm just going to skip ahead. I'm going to evaluate my next 2 points, but I'm just going to tell you what they are. So f prime of 0.25 is -0.8789, which is less than 0, so that's minus. So it's a big minus sign in here. And finally, f prime of 2, that's going to give me 180, which is greater than 0, which is positive. All right, I've set up my number line. I have all my regions. What I'm going to do is identify the local max and min now. Notice at -1, we're increasing, and then we're decreasing. So that's a local max. So I'm going to mark that here, -1. We have nothing happening at 0. And then at +1, we are decreasing, and then we are increasing, which means that's a local min. So we have our max here, and we have a min here. Now I left this blank open because local maxes and mins are points. So as a point, they need an x value. They also need a y value. So what you have to do is you need to go back and plug, this is an actual point, so you need to plug this x value into the original function. Recall that the original function is 3x to the 5th minus 5x cubed. So if you plug 1 into this function here, you're going to get -2. And then when you plug -1 into this function, you're going to get a +2. So these are my local extrema. We are increasing and decreasing. It's good to write down these intervals. So up here we see that we're increasing from -infinity all the way to -1. And we continue increasing from 1 to infinity. We're decreasing from -1 to 0, and then again from 0 to 1. Now you could combine these two and just write -1 to 1 as long as 0 is okay, because again what we're doing is kind of jumping over 0 here, and that's kind of it's a safety net, like what happens if our function didn't actually exist at 0. But since it does and it's a polynomial, you could rewrite it like that. You'll see in other videos where we actually have to skip over something like this. Alright, so first derivative test is done. We have all the information we need. Let's move on.